Hi everyone, this is Sridhar Chintala, Assistant Professor of Physics, ABV Government Degree College, Janagam. So in this present video lecture, I am going to discuss about the alpha scattering formula and Rutherford atomic model. And this comes under the BSc Physics third year. The paper titled as Modern Physics in the sixth semester, and this topic is in the first unit, the inadequacy of classical mechanics, atomic spectra and models, and unit 1, atomic spectra and models. This is the famous scientist, the Rutherford, Ernest Rutherford, and the pictorial diagram which was given by Rutherford, and the alpha ray experiment, alpha scattering experiment figure, and the nucleus. So as far as the Rutherford alpha scattering experiment is concerned, the experimental setup is consisting of a fine pencil of alpha particles, that is helium nuclei, each with a charge of plus 2e, was obtained from a radioactive material like radium or radon by placing it in a narrow tunnel-like opening in a lead block as shown in figure. So the particles are emitted in all directions, but only those come out which are along the axis of the opening. So here, we'll take the annotation. So this is the figure which is showing the experimental setup for the Rutherford scattering experiment. So this is the lead block in which the source of the alpha particle is placed, and it emits the alpha particles in all directions, but only those alpha particles which are along the axis of the what is called the along the axis of the what is called the emitter, they come out and fall on the target material. So here we are placed a gold foil as a target material, and the alpha particles which are coming from the lead block are fall on the gold foil, and they scattered in all directions. So some of the particles are passed through the gold foil, and some of the particles are scattered back. So depending upon the nature of the scattering, so nature of the interaction of the alpha particle with the gold foil or the atoms of the gold, so they are scattered in all directions, and the scattered alpha particles are captured by a fluorescent screen which was placed surrounded by the gold foil. So this is the experimental setup. The experimental setup consisting of a lead block in which the source of alpha particles is placed, and a gold foil which is the target material, and all these scattered alpha particles are collected by a fluorescent screen or observed by a fluorescent screen, and the alpha particles are emitted in all directions, but only those come out which along the axis of the opening. So thus they confine to a narrow beam. This beam is now made to fall on the gold foil G, and a fluorescent screen was placed behind the gold foil. The alpha particles passing through gold foil produces flashes on the fluorescent screen. So this is how the experimental setup is done. So there is a source of alpha particles in which these there is a lead block, and in which a source of alpha particles is placed, and this alpha particles source is emitting the alpha particles, and a fine beam of alpha particles is coming out of the fine hole of the lead block, and they fall on the target material, that is the gold foil, and some of the alpha rays passing through the gold foil, and some of the alpha rays scattered back, and these few of the alpha particles scattered without any deviation, and some of the alpha particles scattered passing through the gold foil and scattered in different directions. So this is how the model was developed by Rutherford. So he thought that there is this nucleus which is at the center, and the electrons are surrounded by it. So the alpha particles are deflected or deviated like this. So if the alpha particle is closer to the nucleus, they deviated more, and the alpha particles which are far away from the nucleus, they come with less deviation, and even without any deviation if they are far away from the nucleus of the atom. So Rutherford made the following observations from his experiments. Most of the alpha particles went straight through the gold foil and produces flashes on the screen as if there were nothing inside the gold foil. So most of the particles went straight through the gold foil. That means there is no deflection at all. And few particles collided with the atoms of the foil, which have scattered or deflected through considerable large angles. And few particles even turned back towards the source itself. So most of the alpha particles went straight through the gold foil without any deviation, and fewer particles are collided with the atoms of the foil and have scattered with considerable large angles, and some of the particles, a few particles even turned back towards the source itself. So these are the observations made by the Rutherford, and from his observations we can analyze that the reason is that the electron, due to their small mass, are not in a position to bring about large deflections of alpha particles. So here alpha should be there here. If you want to close it, you can write alpha. So here alpha should be there. So it is, where is it? This one, alpha. So alpha particles So the reason is that the electrons, due to their small mass, are not in a position to bring about the large deflection of alpha particles. In fact, the electrons may be deflected rather than alpha particles. Actually, the alpha particle should be subjected to very feeble force of repulsion in different directions by the charges spread throughout the mass. In this way, the net deviation of alpha particle should be negligible, small, thus no large-scale scattering is possible in accordance with the Thomson model. And the detailed experiments by the Giger and Marsden showed that large angle scattering can be expected by assuming that a massive point charge exists at the center of each gold atom, as shown in figure the earlier. So before Rutherford, what scientists were thought of as the nucleus is consisting of, the atom is consisting of electrons which are spread all around the atom, and there is no such a center as a nucleus as formulated by or assumed by the J.J. Thomson. So prior to the Rutherford experiment, there is a model called the Thomson model, which was exist at that time. So according to, if the electrons are scattered, electrons are distributed along uniformly in the atom, there must be a deviation due to the electrons for the alpha particle. So as far as the alpha particle deviation is concerned, actually alpha particle is a positive one and electron is a negative one, so that there must be an attraction. But these electrons are, these alpha particles are scattered by the atom, since that means it must consisting of a positive charge. So actually the alpha particle should be subjected to very feeble force of repulsion in different directions by the charges spread throughout the mass. So in this way, the net deviation of alpha particles should be negligibly small, thus no large-scale scattering is possible in accordance with the Thomson model. So the detailed experiments by Geiger and Marsden showed that the large angle scattering can be expected by assuming that a massive point charge exists at the center of each gold atom, as shown in figure. So that means the Rutherford experiment confirms that there is a central massive point that is called the nucleus uh, that was came to existence after the Rutherford experiment. So Rutherford's nuclear atomic model. So Rutherford in 1911 proposed a new model of an atom, that is, it consisting of a nucleus. According to this model, a positive charge of the atom, instead of being uniformly distributed throughout the sphere of atomic dimensions, it is concentrated in a very small volume, that is less than 10 to the power of minus 13 centimeters diameter. Sorry, 13 10 to the power of minus 13 meters in diameter. So at its center. That means according to Rutherford's nuclear model, there must be a positive charge of the atom which is centered at the center of the atom instead of being uniformly distributed throughout the sphere. And this central core, now called the nucleus, is surrounded by a cloud of electrons which makes the center atom electrically neutral. So on the basis of Rutherford's nuclear atomic model, the large scattering of positively charged alpha particles can be easily explained. So from the experimental observations of Rutherford, what he was observed that there is a large scattering of alpha particles from the gold atoms. That means in order to repel the positively charged alpha particles, there must be a positive charge which is strong enough than the alpha particles, and that must be a nucleus. So based on the Rutherford's nuclear atomic model, the large scattering of positively charged alpha particles can be easily explained. So the reason of the large angle scattering is the mutual repulsion, that is as per the Coulomb's law, between the alpha particles and the concentrated positive charge on the nucleus. That is, the alpha particle experiences a repulsive force which continues to increase according to the inverse square of the distance between alpha particle and the nucleus. This was the model developed by Rutherford, and it is called Rutherford's nuclear model. And according to Rutherford's nuclear model, there must be a positive center called nucleus, and there must be a repulsion between the alpha particle and the center of the atom, that is called the nucleus of the gold atom. So when an alpha particle approaches the positively charged nucleus, it experiences a great repulsive force and gets deflected to much greater angles. So the alpha particles which are sufficiently far away from the nucleus, they pass through the empty space without an appreciable deviation, as most of the volume of the atom is empty. So here the force between the electron and alpha particle is ignored. And the drawbacks of the Rutherford nuclear model, the following are the drawbacks of the Rutherford's model. One is the stability of the atom as a whole and the distribution of electrons outside the nucleus. So as far as the Rutherford nuclear model is concerned, an atom is consisting of a positive center which is called a nucleus, so around which the electrons are revolving in circular orbits. So the Rutherford atomic model, the Rutherford nuclear model for the atom failed to explain what are called the stability of the atom as a whole and distribution of electrons outside the nucleus. So as far as the stability of the atom as a whole is concerned, the electrons are surrounding the nucleus at rest. The equilibrium conditions of the system cannot be reduced by electrostatic forces between positively charged nucleus and negatively charged electrons outside the nucleus. So this is one of the difficulty of the Rutherford's atomic model or Rutherford's nuclear model. And then if you consider, as an example, if you consider the helium atom. So the helium atom consisting of two protons and two electrons. So outside the nucleus, the electrons are having a charge of minus E each, and inside the nucleus there are two protons with the plus 2e. So suppose the two electrons are symmetrically placed at a distance of r, small r, from the nucleus as shown in figure. So this is the situation of an alpha particle. So here, so this is the alpha particle, and this is the electrons surrounded by the alpha particle. So that means the helium nucleus. So this is the nucleus, the helium atom. This is the nucleus, and the electrons are surrounded by the helium nucleus. So if you consider the force of repulsion between electrons and the force of attraction between the positive nucleus and electron, so the force of attraction between the nucleus and each electron, if you consider, so that is given by E into 2E divided by 4 pi epsilon naught into r square. Actually, this must be here and this must be here. I think I will make the correction. Okay, where do we go? Should go here. Okay, right. So this must be here and this must be here. No, right. Right. So when you consider the helium as an example, so it consisting of two protons and two neutrons, and two protons at the center of the nucleus, and two electrons are revolving around the nucleus of the helium atom. So if you consider the force of attraction between the nucleus and electron, that is given by 1 by 4 pi epsilon naught into q1 q2 by r square, that is E into 2e by 4 pi epsilon naught into r square. So, and the force of repulsion between the two electrons, if we consider, they are separated by a distance of 2r. So E into E divided by 4 pi epsilon naught into 2r whole square. So if you calculate the force, this shows that the attractive force is 8 times greater than the repulsive force. As the forces do not balance each other, the electrons will fall into the nucleus and thereby destroying the stability of the atom. So as far as the nucleus is concerned, if you speak about the stability, so the force of repulsion and the force of attraction, when you consider, the force of attraction is 8 times greater than the force of repulsion. That means this electron should go inside, approach the nucleus and fall into the nucleus, and by destroying this stability. So this is one of the difficulty which could not be explained by the Rutherford model. And to overcome the difficulty of the stability of atom, Rutherford proposed. So in order to explain that the stability of the atom, Rutherford proposed that the electrons might be assumed to revolve around the nucleus with such a speed that the outward centrifugal force balances the net electrostatic force of attraction towards the nucleus. So before the Rutherford model, the positive charge and negative charge was assumed to be distributed uniformly throughout the atom, but the Rutherford scattering experiment suggested that the nucleus is the atom is consisting of a nucleus which is placed at the center of the atom, and the whole charge, that is the positive charge of the atom, is concentrated at the center. So when you assume like that, the stability of the atom is concerned, if the electrons are at rest, so when the force of attraction between the alpha particle and the electron, and the force of attraction between the force of repulsion between the electron and electron, if you consider for a helium atom, the force of attraction is 8 times greater than the force of repulsion, so that the electron will be attracted towards the nucleus and will fall into the nucleus and thereby destroying the stability of the atom. So if that is the case, the stability should be destroyed, but the atom is stable uh, without any destruction. So to explain that, to overcome the difficulty of stability of atom, Rutherford proposed that the electron might be assumed to revolve around the nucleus with such a speed that the outward centrifugal force balances the net electrostatic force of attraction towards the nucleus. That means the revolving of electrons of the revolving of the electrons around the nucleus comes into the picture of the Rutherford model. So in this way, Rutherford introduced the planetary model of atoms, just like a solar system in which planets revolve around the central heavy sun. Thus, for an electron having a charge -e and mass m revolving in a orbit of radius small r with velocity v around the nucleus with a charge Ze, we have so E into Ze by 4 pi epsilon naught into r square is equals to m v square by r. So this is the force of attraction between the nucleus and the electron, and this must be equal to the centrifugal force, the outward centrifugal force. So this was explained by the planetary model of atom by Rutherford in order to overcome the difficulty of the stability of atom. So from this expression, it can be concluded that an electron can rotate in an infinite number of orbits, and Rutherford's idea of revolving electron leads to a serious difficulty from the point of view of the electromagnetic theory. So before this, the electromagnetic theory were already existed. The existed electromagnetic theory suggests that a moving charge can radiate energy. So as the electron is moving around the nucleus, it must radiate energy. So as it is moving continuously, it must radiate energy continuously. So according to electromagnetic theory, a revolving electron should radiate energy continuously, and this energy can come from the atomic system itself. So this is another difficulty of the revolving electron, and this is the case. So this is the nucleus of the atom, and the electron is revolving around the nucleus. So as it is revolving around the nucleus, it has to radiate energy. As it is radiating energy, it must lose its energy, and it follows a helical path and goes on going and falling in the nucleus by emitting a photon. So that means a continuous radiation emission must be taking place. So according to Rutherford model, so due to continuous loss of energy, the electron will gradually approach the nucleus by spiral path and finally fall into the nucleus. So hence the revolving idea of the electron destroys the stability of the atom. That is the very purpose of which it was postulated. So to explain the stability of atom, Rutherford postulated that there must be electrons revolving around the nucleus. But according to the electromagnetic theory, a moving charge produces a energy, that is electromagnetic energy, a photon. That means as it is emitting energy, it must lose the energy. So due to the continuous loss of energy, the electron will gradually approach the nucleus in a spiral path and finally fall into the nucleus, thereby uh, uh, again giving a contradiction or the what is called the difficulty of the stability of atom. So obviously either the Rutherford's nuclear atom model with the revolving electrons is defective, or the classical electromagnetic theory fails to explain the present case. So in order to explain this, we have to have another model. So this problem was actually solved by Niels Bohr in 1913 by admitting the failure of classical theory and by applying quantum theory to the Rutherford nuclear atomic model with revolving electrons. So this is the Rutherford atomic model. As far as the Rutherford atomic model is concerned, So the alpha particle experiment suggests that there must be a central core which consisting of the positive charge of the whole positive charge of the atom, and that is called a nucleus, and around which the electrons are revolving in the circular orbits. So that is the Rutherford model, and it fails to explain the stability of atom, and it fails to explain the what is called uh, so it fails to explain what is this. It's not coming. So distribution of electrons outside the nucleus and the stability of the atom as a whole, it fails to explain. And in order to overcome the difficulties, Bohr's model comes into picture. And this is the Rutherford alpha scattering experiment for the scattering cross section. So in order to calculate the scattering cross section, so consider a nucleus of charge Ze stationary at a point n and an alpha particle of mass m and velocity v0 approaching along the direction AO as shown in figure. So as alpha particle moves, it comes closer to the nucleus and experiences a repulsive force. With this result, the velocity of alpha particle decreases. So in the absence of repulsion, it would have followed a straight path, but due to the Coulombic force of repulsion, it follows a hyperbolic path AB with the nucleus as its focus. So this is the figure which is showing the scattering of alpha particle by a nucleus. So this is the nucleus which is supposed to be at rest at a point n, and alpha particle is approaching the nucleus in this path. So we may assume that alpha particle is approaching like this and alpha particle is approaching like this in these directions. So as it is coming closer to the nucleus, it experiences a repulsive force. So as a result of repulsive force, it follows a hyperbolic path EAB and with the nucleus as its center. So for the hyperbola, the center of the hyperbola is the nucleus. So the velocity of the particle as it approaches the nucleus, the velocity of the particle decreases. So in the figure, the line AO and PO are the asymptotes of the hyperbola and present approximately the initial and final directions of alpha particle. In this part of the journey, AC, the velocity of alpha particle goes on decreasing, while in the path CB, its velocity goes on increasing till again it reaches its original velocity. So this is our figure. So in this figure, this is AC and this is BC. So from A to C, the velocity decreases, and C to B, the velocity increases. From A to B, if you consider, so as it is approaching the nucleus, the velocity gradually decreases, and from here the velocity again increases as it till it reaches the value of initial velocity, and the asymptotes of this what is called the hyperbola AO and PO, which represents the initial and final directions of the alpha particle, and the velocity is decreases along AC and velocity increases along CB. So this is the alpha scattering, and this P is called the closest distance of approach, called as the impact parameter, and this is the scattering angle. So let us discuss in detail and try to derive an expression for this scattering angle. So in figure 6, P is the perpendicular distance from the nucleus N to the original direction of the alpha particle, and the distance is called as impact parameter. The angle of deviation or scattering of alpha particle is evidently theta. So to derive an expression for theta, we proceed as follows. First of all, consider the case when alpha particle is directed straight towards the nucleus so that P is equals to 0. That means the closest distance of approach is equal to 0, means the nucleus is approaching directly onto the nucleus. Sorry, alpha is particle is approaching directly onto the nucleus. So in this case, alpha particle will be stopped at a distance b from the nucleus due to repulsive force and traces its reverse path. That is, theta is equals to 180 degrees. So in the figure we have a nucleus here and alpha particle is approaching in this manner, and as it is coming closer to the nucleus it experiences a repulsive force, so it repelled back like this. So the distance, the closest distance of approach is called the impact parameter P. So in the first case what we are considering is, this is the axis of the nucleus. So what we are considering is the alpha particle is approaching along the axis of the nucleus. So that means the P is equals to 0. P is equals to 0 means the alpha particle is approaching in this direction. So if this is the case, so the alpha particle will be stopped at a distance called small b, and it is reflected back. That means the path of the alpha particle is traced in reverse path. So that means the angle theta, the scattering angle, is equals to 180 degrees. So in general what we assumed is an alpha particle is coming in this direction, and due to the repulsive force it experiences a repulsive force and it traces a hyperbolic path, and if we extend like this, the direction of this asymptote gives the direction of the final direction of the alpha particle. So this must be the scattering angle we assume. So if you consider P is equal to 0 case, that means the alpha particle is coming straight to the nucleus, and due to the repulsive force it again traces back. So in this case the theta is 180 degrees. So first of all we consider the case when alpha particle is directed straight towards the nucleus so that P is equals to 0. So in this case alpha particle will be stopped at a distance b from the nucleus due to the repulsive force and traces its reverse path, and theta is equals to 180 degrees. So actually this is theta. So here this must be theta. Theta is equals to 180 degrees. So the distance b is known as the distance of closest approach, and the value of b can be determined by considering the principle of conservation of energy. So what is the distance of closest approach is called the beta. So we can calculate the value of b by using the conservation of energy, principle of conservation of energy. So the electrostatic potential at a distance b due to nucleus is given by, so this is Z into E divided by 4 pi epsilon naught into B. So this is the potential due to the nucleus at a distance small b, and hence the potential energy of the alpha particle at a distance small b from the nucleus is given by, so this one is the potential, so V into Q, the potential energy. So ZE by 4 pi epsilon naught into B into 2E is equals to 2ZE square by 4 pi epsilon naught into B, where 2E is the charge of the alpha particle. So this is the case when P is equal to 0. That means the impact parameter, the perpendicular distance between the approach of the alpha particle with the nucleus, that is equals to 0. So in that case, the scattering angle is 180 degrees. So the closest approach, the distance of closest approach B can be calculated from the principle of conservation of energy. So when the alpha particle is momentarily stopped at a distance B, its kinetic energy of m v naught square is completely converted into its potential energy. So this is the situation. The kinetic energy is equals to the potential energy. The kinetic energy is half m v naught square is equals to 2z e square by 4 pi epsilon naught into b. And from this we can write that the value of b as the closest distance of approach b is equal to z e square by pi epsilon naught into m v naught square. So this is the distance where the alpha particle is stopped by the repulsive force of the nucleus and traces reverse path. And the above case is not possible in actual practice sin, and hence we consider the case in which p is not equal to 0. So the straight going to the nucleus, straight going of the alpha particle to the nucleus is not possible in actual practice. So in this case, we consider the case as p is not equal to 0. So in this case, the alpha particle is deflected through an angle theta which is less than 180 and traverses a hyperbolic path. So when you consider p is not equal to 0, the scattering angle is not equal to 180. That is, the scattering angle is less than 180 and it traverses a hyperbolic path. And let v be the velocity of alpha particle at the vertex C, and the angular momentum of alpha particle when it is at A is m v naught p, and the angular momentum we can write as the formula from the formula as mass into velocity into distance. So mass is m, velocity is v naught, initial velocity is v naught, and the distance is v. That is the distance from the nucleus to the alpha particle is p, and the angular momentum of alpha particle when it is at C, that is mv into nc. So in the figure we have like this. Here the nucleus is there, and these are the two asymptotes, and this is the hyperbola. This is A, B, and this is the center C, and this is O, and this is N, and this is P, and the distance from here to the first asymptote is the dB. So when p is not equal to 0 case that we are considering here, so the angular momentum of the alpha particle when it is at A, so when it is at A, the angular momentum is given by m v naught into p, and the distance is p here, and the angular momentum of alpha particle when it is at C, so here when it is at C, the angular momentum is given by mv into nc. So the mass into velocity is v and the distance is nc, and from the principle of conservation of angular momentum, this must be equal to this. So that means m v naught p is equal to mv into nc, and this m cancel. So we have v naught p is equals to nc, and v into nc, and v is equals to v naught p by nc. Here v naught is the initial velocity which is already known, and p is the impact parameter, and nc is the distance from the center of the hyperbola to C. So v is equals to v naught p by d. So this is the value of the velocity at C, velocity of the alpha particle at C. So where the distance nc is equals to d. So the kinetic energy of alpha particle when it is at capital A is half m v naught square, and kinetic energy of the alpha particle when it is at C is half m v square. So this is from the angular momentum and this is from the energy. So the potential energy of the alpha particle when it is at a C is ZE into 2E by 4 pi epsilon naught into D. So ZE is the charge of the nucleus and 2E is the charge of the alpha particle divided by 4 pi epsilon naught into D. So this is 2ZE square by 4 pi epsilon naught D. By the principle of conservation of energy, so initially the alpha particle is having only kinetic energy. When it is approaching the nucleus, it is having the kinetic energy as well as the potential energy. So here it is the half m v naught square is equals to half m v square plus 2z e square by 4 pi epsilon naught d. So this is the potential energy and this is the kinetic energy when it is at point C, and this is the kinetic energy when it is at point A. So from the principle of conservation of energy, the total energy must remain constant. So from this equation, what we can write for V as V square is equals to V naught square minus ZE square by pi epsilon naught into MD, and V square is equals to V naught square minus, we already have an expression for the this one, B for B. So it is B V naught square by D. So V square is equals to V naught square minus B V naught square by D, and this is V naught square into 1 minus B by D. So from the expression of the what is called the angular momentum expression, M V naught P is equals to, we have M V D. So from this equation we can write as the V is equals to V naught P by D. So that we are substituting here, and we have V square is equals to V naught square into 1 minus B by D, and substituting the value of V from equation 2 in equation 3 we get, so this is the value of V from 3, V is equals to V naught P by D. So V naught square P square by D square is equals to V naught square into 1 minus B by D, and this V naught square is cancelled, and P square is equals to D square into D minus B by D, and square D cancelled, so it is P square is equals to D into D minus B. Okay. So in the previous slide we have V is equals to, we'll write here, we'll keep that aside, this V is equals to V naught P so V is equals to V naught P by D. This is one equation, and we have P is equals to D into D minus B, the other equation. Sorry, this one, P square is equals to D into D minus B. Here P square is there, and so from the properties of hyperbola we have, these are the two equations we should keep in mind. And from the properties of the hyperbola we have the eccentricity of hyperbola as E is equals to sec phi, and focal length ON is equals to E into OC, that is A sec phi, and we know that ON is equals to P cosec phi, and a sec phi is equals to p cosec phi, or a is equals to p cot phi. And from figure, NC is equals to NO plus OC. So we have a figure like this. This is the nucleus, and I think we should keep this figure always here. So this is C, and this is A, and this is B, and this is N, and this is O, this is P, and this is D. Sorry, this is B, and this is D. I think this is also D. I think. Okay. So from figure, what we can write as NC is equals to NO plus OC, and this is D is equals to A sec phi plus A, where NO is A sec phi. So here we have phi, the angle, and this is also phi. So D is equal to A sec phi plus A. What is OC is A, this one is the A. So, and this will be A sec phi. So D is equals to A into 1 plus A sec phi, sorry, A into 1 plus sec phi, or D is equals to A, if you substitute the value of A here, from here, P cot phi into 1 plus sec phi. So D is equals to P into cot phi plus 1 by phi, and this is cot phi plus 1 by sin phi. How do we got this? Right. So here cot phi into sec phi, cot phi plus cot phi into sec phi is 1 by sin phi, and this is cot phi into sin phi plus 1 by sin phi, and P is equals to, this is cos phi plus 1 by sin phi, and this is 2 cos square phi by 2 by 2 sin phi by 2 into cos phi by 2. So when you are writing 2 here, I am dividing and multiplying with the 2. So this will be square and cos will be cancelled, and 2 cancelled, and this is what is called P into cot phi by 2. So D is equals to, the value of D is equals to P into cot phi by 2. Right. So D is equals to P into cot phi by 2, and substituting this value of the value of D in equation 4 we have. So this is equation 4, P square is equals to D into D minus B. So this is D is equals to, so P square is equals to P into cot phi by 2 into P cot phi by 2 minus B, and this P square and P is cancelled. P is equals to cot phi by 2 into P cot phi by 2 minus P. So this is expanding this. So P into cot square phi by 2 minus B cot phi by 2, and B, for B if you want to write, this is, so this B goes this side and P comes this side. So P cot square phi by 2 minus P, that is if you P taken as common, into cot square phi by 2 minus 1 by cot phi by 2 is equals to P into cot phi by 2 minus 1 by cot phi by 2, that is tan phi by 2. And if you write in terms of cos and sine, this is cos phi by 2 by sin phi by 2 minus sin phi by 2 by cos phi by 2, and take the LCM. So this is sin phi by 2 into cos phi by 2 in the denominator, cos square phi by 2 minus sin square phi by 2 in the numerator. So B is equals to 2P cos phi by sin phi, and that is 2P into cot phi And if you write for cos tan phi, it is 2p by b. So this is the one more relation. This is the what is called tan phi is equals to 2p by b. So now the deflection angle for the alpha particle is given by theta is equals to phi minus 2 pi, pi minus 2 pi. So here the angle is theta. The angle is theta here, and this is the total 180 degrees. And here we are having pi and pi. So that means theta is equals to pi minus 2 pi. Theta is equals to pi minus 2 phi. And this is phi by 2 is equals to pi by 2 minus phi. And if you take the cot theta by 2 is equals to cot pi by 2 minus phi, and this is cot theta by 2 is equals to tan phi, and this is one more equation we are having. So from 6 and 7, if you write this, if you equate these two, this is tan phi and this is also tan phi. So cot theta by 2 is equals to 2p by b, or tan theta by 2 is equals to b by 2p. And we have b is equals to from the kinetic energy and potential energy relation, b is equals to z e square by pi epsilon naught into m v naught square. So if you substitute the value of b in this equation, we have tan theta by 2 is equals to z e square by pi epsilon naught into m v naught square into 2p. And here we are having 2. So if you want to write in terms of 4 pi epsilon naught, so we're dividing and multiplying with 2. So 2 into z e square by 4 pi epsilon naught into m v naught square into p. So this equation determines the scattering angle. So this is the expression for the scattering angle. So now let us see the, what is this? What happened? Right. So annotation is calling. Clear all drawings. Right. So next slide. Right. So now we shall consider the case when a narrow beam of alpha particles incident normally on a thin foil of the scatterer as shown in figure. So this is the what is called the target material. So alpha particle is falling on the target material normally, and it is passing through it and scattered in all directions. So now let T and N be the thickness and number of atoms per unit volume of the scatterer respectively. So the scattered particles are detected by means of scintillations produced by them on a fluorescent screen S. Let Q be the total number of alpha particles that strike the unit area of the scatterer, and our aim is to calculate the number of particles N that are scattered through an angle theta and strike unit area of the screen at a distance small r. So let Q be the total number of alpha particles that strike the unit area of the scatterer, and our aim is to calculate the number of particles that are scattered through an angle theta and strike unit area of the screen at a distance small r. So in order to do so, it is clear that any alpha particle whose initial velocity would bring it within a distance p of the nucleus will be deflected through an angle theta. So in order to determine the probability that an alpha particle would come within the distance, we imagine a circle of radius p drawn around each nucleus. So actually we have the figure, again I am drawing the figure. So this is the nucleus, this is the axis. So this is how the alpha particle is approaching, and Due to the repulsion, it experiences a hyperbolic or the parabolic path, and these are the two asymptotes. Sorry. So in this way, so these are the two asymptotes. So this is phi, this is phi, and this is theta. So here is the nucleus. The alpha particle is approaching like this. So this alpha particle must be interacted when only when this comes within a distance of small p. So that means we are assuming a circle around each nucleus with radius as p. Radius as p. In order to determine the probability that an alpha particle would come within this distance, we are assuming we are imagining a circle of radius p drawn around each nucleus. So this is the circle around which each nucleus, and the area occupied by all such circles in unit area of foil is pi p square into nt. So this is the area, and T is the thickness of the foil, and N is the number of molecules or the number of atoms. So the area occupied by all such circles in unit area of foil is pi p square nt, and the probable number of alpha particles coming within the distance of an impact parameter p of the nucleus is given by pi p square nt q. So q is the total number and this is the area. So if you multiply the area with the total number, you will get the probable number of alpha particles coming within the distance of an impact parameter p of the nucleus given by pi p square into nt into q. And it's the number of alpha particles having an impact parameter between p and p plus dp is given by, so d of pi p square ntq is equals to 2 pi pt nq dp, and thus the number of alpha particles scattered between angles theta and theta plus d theta is 2 pi pt nq dp. And from equation 8 we can write p is equals to 2z e square by 4 pi epsilon naught into pm v naught square into cot phi by 2, and from that we can have the value of dp as dp is equals to, we are differentiating this equation, so 2z e square by 4 pi epsilon naught into m v naught square into minus 1 by 2 cosecant square theta by 2 d theta. So substituting values of p and dp in the equation, we have, so putting these values in equation 9, we have the number of alpha particles scattered between theta and theta plus d theta as 2 pi into, so this is p value, t and q into this is dp value. So if you substitute those values in this equation, so we get this one. So all these alpha particles will strike the screen within a circular annulus of radius, area dA, which is given by dA is equals to 2 pi r sine theta into r theta. So that is the circumference into the radius, and this will be dA is equals to 2 pi r square sine theta into d theta, and dA will be 4 pi r square sine theta by 2 into cos theta by 2 d theta. Here we expanded the sine theta as 2 sine theta by 2 into cos theta by 2. So dA is equals to 4 pi r square sine theta by 2 into cos theta by 2 into d theta. So the number of alpha particles n striking the unit area of the screen is given by, now n is equals to 2 pi into 2z e square by 4 pi epsilon naught square epsilon naught into mv naught square into cot theta by 2 t n q into half cosecant square theta by 2 into d theta into 2z e square by 4 pi epsilon naught mv naught square. So actually there is a negative sign here. So here we are only consider the number of particles. So the negative sign is ignored due to the magnitude consideration. So divided by 4 pi r square sine phi by 2 into cos phi by 2 into d theta. So this is the total area, and this is the number of particles which are falling on the screen, which strike the screen within a area dA. So if you want to calculate the number of particles per unit area, we have to divide the number by the value, so the area. So we will get n is equals to TNQ into 2Z E square whole square into 4 into divided by 4 into 4 pi epsilon naught whole square into R square m V naught square whole square into sine to the power of 4 theta by 2. So this is the equation number 10. The equation number 10 gives the value as the Rutherford scattering formula. That is the number of alpha particles which are falling on the screen after passing through the gold foil. So from that equation we can conclude that the total number of scattered particles per unit area is proportional to the inverse of sine power 4 theta by 2 and proportional to the thickness of the scattering material and the square of the atomic number proportional to the square of atomic number of the scatterer and inverse of the square of the kinetic energy of the particles. So this n, the equation 10 gives the Rutherford scattering formula, and this n gives the total number of scattered particles per unit area, and the number is proportional to 1 is the fourth power of sine theta by 2 and inversely proportional to fourth power of sine theta by 2 and the proportional to the thickness of the scattering material and square of the atomic number of the scattering material, and it is inversely proportional to the initial kinetic energy of the alpha particles. So this is about the Rutherford's scattering and scattering formula and alpha scattering experiment. So thank you for your attention. Thank you for your patient listening. Thank you.